Welcome to a new bare metal embedded programming series. I will go through this schedule to show you what this video is all about. So, first I would like to thank you for watching the video, I guess. So, what we do here, we develop bare metal software for ARM Cortex M3, and we will be showcasing simple bootloader from scratch. So we're gonna have a series of videos in which we show how we build from scratch a bootloader. The code that we'll use, it's a bare metal code, and we develop everything, let's say, in the videos. So we'll go into details in a series of future videos, and but in this video it's just a presentation of a stable release, let's say. So we're going first to meet our controller. Now we're going to use a blue pill board, and we'll look at the controller, and we'll look at the memory layout, and then the actual work. I think we're going to showcase the following things here. So we have two independent programs that we're going to call P0 and P2. These are completely independent programs. They're built differently. They're built separately, one to another. And we show the linker script for each of them to indicate the place in the microcontroller memory. And then we place the P0, and that's the first program. We put it somewhere in the memory in such a way that it is executed automatically after reset. So after reset we expect P0 to be run, and P0 can receive the binary of P2, for instance, and write it into the flash at the correct address, and P0 then can jump to execute P2 code, P2 being the program 2. And then for doing all this, we actually built a simple Python console which allows the communication with the laptop, and basically allows the steering of the P0 program and sending the binary for the program 2. So this is what you should expect in this video, and now we're going to each of these points. So let's meet our controller. So our controller, it's this one, STM32F103XX family, and for instance now I have here the low density device which has 32 kilobytes of flash and 10 kilobytes of RAM. So this is the controller that we are interested in, and this is this is our platform for now. So this is the controller, I guess. Now we're going to jump to see the memory better. Okay, so this is the memory mapping of the controller, and we're going to be using this to explain several things now, but in the future videos we're going to into larger details for the sake of better explaining everything. So in this video you should expect like a presentation pretty much of a stable release. We're not going to explain everything in this video. It's going to be the future videos which hopefully will answer your questions more. But now you're kind of seeing what to expect if you go through the future videos, something like that. So yeah, it's interesting. I think I like to propose actually this kind of presentation in which the viewer, which is you, will know beforehand where the presentation goes. So if you watch this video and you don't like it, then probably doesn't make sense to follow the other videos, kind of. So right, let me see where I am. Right, so we just saw the controller. We have a memory layout now, So let's look at these two independent programs. P0 is going to be the bootloader basically, and P2 it's going to have, let's say, prerogatives of an application. So, but for now, these are completely independent programs. Right, let's look at the linker script for each of them. Okay, so this is the linker script for the program 0, and you can see, let's go through the linker script. So in this linker script we define this the memories that we're going to have. So for now you're interested only in RAM and in flash, and this is the RAM for P0, and you can see that we place the origin at this 0x200 whatever. Why we did it? So let's look at the memory layout, and you can see that the SRAM starts at this address 0x20000 whatever. Okay, so this is where the RAM starts. So P0 has the RAM here at the very start of the RAM, but we also define for P0 that the RAM has a length of 2 kilobytes. Okay, if you remember previously, the length of the size of the RAM in this controller is 10 kilobytes, but we're going to take only 2 kilobytes out of all those 10 kilobytes, and those 2 are reserved for program 0. So as far as program 0 is concerned, the controller has only 2 kilobytes. That's what we're telling here. So we actually have a controller which has some memory, but we would like this, it's like a piece of land that we would like to divide between two families, let's say, so, or two countries. So this first country, which is P0 country, is going to have 2 kilobytes of memory, of RAM memory, okay? And it goes to flash. The flash for the P0 starts at 0x8 whatever zeros there, and has a length of 5 kilobytes. Okay, so the reason for that, so I said the start is at here, 0x8. So this is alias to 0 basically. So as you can see here, alias to flash or system memory depending on the boot pin. So the boot pins are in such a way that this one sorry, that this one is alias to the 0, to the start of the memory. And if you remember, the size of flash of this particular controller is 32 kilobytes, but for P0 program we're going to take 5 kilobytes. So this is the memory that we, let's say, gave to P0. So P0 starts at this RAM, at this flash, and has the RAM has this length and the flash has this length. Okay, alright, so this is P0. And then we have the sections. Probably in the future videos we'll be going through these sections and we will explain why are they needed, what's with these sections and how we put them there and whatever. But for this video in particular, this is all that we are interested in. Okay, so now we have the linker for the second program. And for the second program, the same things I'd like to explain. It's the memory for it. So we have here the RAM and flash for the program 2. So it's only now I can see that this name is P1. It's not interested, but yeah, of course I had another program P1, but now I'm showcasing P2, and I guess you might have already seen that this is a kind of a copy paste. So anyway, this functions as the memory definition for the second program, for the program P2. So you can see that the RAM here starts at this address. I mean, this address is well 200 and ends in 800. why this? So where is this 800 coming from? So if you look at this computer, you remember that we had how many? I think 2 kilobytes I think of RAM previously, so that's going to be 1024. This is how many bytes a kilobyte has, multiplied by 2, and we have this 2048, which is 800 in hex. So this RAM starts after the first RAM ends, okay, and the length of this RAM is going to be 8 kilobytes. I mean, that's all we have until we reach 10 kilobytes. Right, so that's for the RAM. And for the flash, you might already have guessed, the flash starts here and has a length of 27 kilo. Why 27 kilo? Because that's 32 kilo without those 5 kilobytes that that P0 had. So you can see that the origin of flash for the P0 program is at 0x800 1400. And where is this number coming from? Oh, well, I think we can do the same thing here. If you remember, we had 5 kilobytes for the flash for the P0 program. So 5 times 1024, it's yeah, 5120, which in hex is 1400. So right, that's 1400 bytes. That's how much flash we have for the P0 program. So the flash for the P2 program starts at this address. Okay, so I think that you can now kind of see how we out of this controller we specified some memory for the first program and then some memory for the second program. And as far as this video series are going, we don't have shared memory for them. We definitely can do that, but so far these programs inside the controller, they're completely independent. They do not overlap. Okay, so we intend to put them both in the controller and then have them working somewhere there, somehow there, and we'll see how we're going to do that. So let's go back to our schedule to see what we should say next. Okay, we are now going to discuss how are the programs executed, basically. Okay, so let's see how it's the first program executed. Let me find the correct documentation for it. And right, so what you should know is that in this let's see, I think this is the programming manual for the controller, and you can see 2 very important, let's say, sentences here, and this tells us what the controller does after the reset. Okay, so when you reset the controller, 2 main things happen. On reset, the processor loads the main stack pointer with the value at this address. So the main stack pointer is being loaded with the value that it takes from this address. Okay, so what we want to do is we want to put at that address, where is that address? Here. It means we want to put here in the very first 4 bytes here, would like to put here the value of the main stack pointer. Okay, and then the second thing is that the program counter says on reset the processor loads the program counter with the value of the reset vector, which is at this address. So these things happen without well, doesn't matter what you do. This is a pretty much hard-coded behavior. Alright, so we will actually put at the address 0 the value of the main stack pointer for the P0 program, and we'll put at the address 0x4 we're going to put the pointer to the startup code. So I'm not going into many details now in this let's say introductory video, but we're going to explain this in the following videos. So what you can see here is that the stack top was loaded here in our special section that we had, and then we had here the pointer to the startup function, and this we put them in an array calling it GD vectors. These GD vectors are, let's say, placed in a special section, and this section is basically put there at the very first thing in this flash P0. So what will end up happening is that after reset, the program 0 is going to be executed. Okay, and then kind of in a similar fashion, we would like to do with the program 2. So everything that the controller does automatically or hard-coded in order to start the program 0, we are going to do something similar in order to start program 1. So we will explain this in the let's say following videos, but now I'd just like to show you how all this thing works. Let me see if I intended anything else to say. Okay, so then P0 jumps to execute P2. Yep, we're going to show that, and also we build a simple Python console which allows steering of the P0 program. So I'm going to, let's say, build all of these programs, and I'm going to show you what happens. What you are seeing now, it's I think it's a blinking of green LED, and it has a certain frequency. The frequency that you're seeing now, it's I think about a second, or let me see, where is that supposed to be defined? Yeah, it's I think this goes every 100 milliseconds, and this one goes for each 300 milliseconds it toggles. So this is something which is specific to the bootloader. When I mean the bootloader, I mean the P0 program, and the P2 program is going to have a different frequency. So you're going to see or know visually when we are let's say in a P0 program, which is the bootloader, or we are in the P2 program, which would be the application. So I'm going to build independently each of them, and then I'm going to flash P0, and yeah, we're going to have a dump of the memory and see that we flashed P0 and there is nothing there but P0, and then we're going to load the P2 with using our, let's say, interface, our Python console, and then we're going to intentionally jump and execute the P2 program, and then yeah, going to reset via usart the P2 and be back in the bootloader. So that's what we're going to do next. So for now, let's build each of our programs. So here, yeah, I mean, how are we going to build it? I'm going to show you. I made a, let's say, we have a make file for each of them. So this is the make file for the P0 program. Probably it's worth showing how the folder, folder structure we have. So let's go through this. We have inside program 0, we have basically, let's say, 2 folders. One of them is with the sources, and with the sources we have the application, we have the COM, and we have the drivers, and we also have the startup. So we have 4 folders here. In drivers we have some developed from, let's say, from scratch drivers for Flash, for I2C, for the MCU, for the SPI we had timer here, and PVM we have a driver for the universal synchronous asynchronous interface. And right here, so it's here inside COM, we kind of have a small UDS service provider, but it's very at the beginning, just barely servicing the communication with the Python console. Right, so these are going to be explained pretty much in future videos, but for now we're just going to show you how this is going to build. So program 2 is very similar to program 0. They're basically copy paste and just modifications here and there. Right, so let's build program 0. Here, in order to build program 0, we will clean everything, and you can see here that inside bin okay, so these my file stuff, these are residual memory dumps. We can go there and just clean them better. So let's go to GD software program 0, and here inside bin we're just going to delete these files. Right, so these are no longer here. We can now have our build of the yeah, clean. It's nothing to be cleaned, and we're just compiling the thing. Okay, so now we have the binary for the program 0. Right, we're going to do a similar thing for the program 2. Well, I guess this one is the thing, and just clean everything here and just build program 2. Okay, so now we have the binary for program 1 and program 2, and what we're going to do now, we're going to flash now we have the binary for program 0 and program 2, and what we're going to do now, we're going to flash program 0. So we are using OpenOCD for this, and let me see how yeah, this is something else. Next, I think I should start that OpenOCD thing. We're going here, open a console, and let's start the OpenOCD. I just have a command here that I'm going to use for this. Right. Okay, so now is listening on this port for whatever. Okay, this seems to be fine, and now we are going to flash the program 0. How do we flash program 0? Oh, here it is. We're going to open this telnet localhost whatever 44, and here we're doing the following things: resetting, flash, write, bank, whatever, mass erase of the thing, and yeah, probably it's now worth just taking a dump of the how am I going to write for the dump? I think I had the command here, probably write bank. No, just it's going to be read bank, I think. Read bank, and now was it a 0 here? Probably just allow me read bank 0 filing. Okay, so this is basically the command read bank 0, and then let's say this would be after mass erase. Okay, so they wrote it here, and now of course it would be interesting to go to this file and just observe that there is absolutely nothing inside the controller. So looking with the plugins with the hex editor, viewing hex, everything inside the controller flash, it's just FF. This is after a mass erase. Okay, so there is nothing running here. This is empty. Right, now we're going to write program 0, and program 0 according to our linker script should be written starting from address 0. Okay, so after we write program 0, we should see here the hex code of the program. Right, okay, let's do that. Let's go to, where was it? Here now we're going to write the okay, so this is going to write our P0 binary. Okay, it was written, and now we're going to have a reset, this is the bootloader going now. I mean program 0. Right, so now it's worth probably just having another read of the message. So this is going to be P0 program. Right, so let's have a look at the flash. How we just called it, P0 program. Let's open and plugin hex editor viewing hex. Alright, so you can see now this is basically this is the hex code of the program, of P0 program. You can basically see here these bytes. These are supposed to be the bytes that we used for the the things that we actually wrote inside the our GD vectors. Okay, so for instance, in order to make sense out of this, what would this be? This is a little endian thing. So this byte here is 0800 and then 200 here, I think. So this one should be, if probably I should not go in these details this early, but going to the GD startup, this should be similar to what we intended it to be here, right? So this is the stack top that we're going to see at the address 0, and and then how are we going to see? So this one is 2000 and then 0800. Okay, so this one should be read first, and then this is with the NDNS thing, and this one here is going to be the address of the startup code for the P0. That's what we're seeing here. Anyway, we're going to do bigger details later regarding this, but anyway, this was read from the controller. And of course, if you go down here, after this amount of bytes, the flash of the controller has nothing in it. Okay, after our bootloader will load the P2 program, we expect at this address to, well, starting from this address, to see the binary of the P2 program, but for now it's not here. Anyway, now it's time to show our Python console, and for that let me go here. This is our GD shell. So this is kind of a script made in Python, and it's somehow inspired from whatever turtle example or something like that. I'm not a Python expert, I just made it work. So what I tried to do here, it's a sort of a like a UDS service provider. What we're going to do, let's start the console here. Where is it? I guess this one should be, and it's Python GD shell.py, running this script, and here we have it. It's a console. We have several commands here. I like UDS 0x11. This is going to be the reset. 0x34. I mean, for this UDS commands, you can look inside the, let's say, Wikipedia or whatever standard you have, kind of trying to copy what happens in the automotive world. So these commands here are, if you were to implement them in a more serious way, they'll be having some protocols or something related to that. But for this, let's say, small purpose that we had here, these commands are doing the following things. Let's try and ask our shell what each command does. So I think that how was that? Question mark and then the for help help UDS, for instance, 0x11. So this one says UDS used to send unified diagnostic message 0x11, that's going to be a reset. And of course we can do it, it's going to reset, we're going to do it later. Okay, so right, what we're going to do now, it's I'm not going to waste too much time and just write the application, write the P2 program. And for that we're just going to the P2 binary folder, this one here, just copy it and put it in that place where we have the console. And the console, let's navigate to that thing here, git bare metal, pi serial here, and I'm just going to paste it here. Paste, replace the final destination. Okay, and now we are hoping that this thing is online, and for that I'm just going to instruct it to write a 0x30. Yeah, this 30x UDS command means download software or something like that. Says for the actual transmission of data, this is 0x36. Okay, so what will happen when the Python script receives this command? Does the following thing. Let's see here. Where is it? Right here. So what we'll do, it will get the size of the file and then we'll transmit this command to the controller, to P0 program, and then after this 36 indicator, it will tell the controller the number of bytes that it will transmit. Alright, the controller will receive this 36 command and then the number of bytes, and then it will erase the flash starting from address 0x1400, the one, this is going to be hard coded. Let's look at the code here inside. This is the P0 program, and where was that implemented? Probably here. Okay, so we have here a sort of a command translator, and when it gets this command 36, it will form the size of the transfer, and then it will erase the flash. So many pages it will erase in such a way that the number of bytes that it will receive should be written on erased pages. And after that it will let's say receive from the controller each byte, and then it will write the byte in the flash, and wait for the next byte. So something like this, we will be having the P2 binary being written in the flash of the controller. So let's go forward with this, just hit enter here. Okay, so it just told us that it got that. Okay, now it's sending the bytes. You can see that blue lights in the USB too. Okay, so it's done. Now it's time for us to, let's say, have another memory dump of the controller and see if anything has been modified. Okay, another P0 as a P2 program. Just going to have this memory dump, and let's have a look at this. Where is the P2 program? Looking with the Notepad++. Okay, there is something. View in hex. Right. So this is the new memory dump. As you can see at the address 1400s, we have the flash being written. So these were written here by P0. P0 wrote this flash, and what you're seeing here, this is basically the hex code of the P2. So all we're going to do now is we're going to jump to execute this code, because currently the program counter runs somewhere around here in this area. This is the code for the P0. It will never reach this area of flash. But now we're just going to execute this code somehow, and yeah, we're going to tell in future videos how that happens. We're basically going to branch here, and I have this is a discussion now to instruct P0 to jump here. How is it going to do it? Well, I just had a simple solution for sake of this video. Yeah, I just invented a new UDS command, which is nowhere in the standard, but it was useful for me. I yeah, called it, let me see how I call it. If you look here at the help, I think you're going to see 0x1a. This 1a means jump to application. Well, I'm just joking. This is no longer UDS, of course. This thing doesn't exist, but for me it's useful because now I have the flash written. I'm still executing P0, but when I send this command, I'm going to jump to execute the other thing. Basically, what I want to do with this bootloader thing is to we're working at a larger project with a sort of a drone, and would like to be able to flash the software in the drone without having the debugger connected. And as far as I can steer this flashing thing from the USART or something like that, it's fine for me for now. Probably going to improve this later, but let's see what this 0x1a does. So inside the Python script, it does the following. Where is this command coming? Wait, 361a. This one is going to send this command 0x1a. Inside the controller, when it gets 1a, okay, it's going to set a flag, and setting a flag, let's say somewhere in the application, this is going to make the branch. I mean, just start executing code from that flash area which was newly written. So now I'm going to just send this command over the, well, in our GD shell, and this is going to be the command, right? Just send it, and you can see that the frequency of the LED, it's different. Well, this is the frequency which tells us that now we are executing the P2 program. Okay, so P2 program has a, let's say, larger delay. Let's go here. We are now in the, let's go to application. This is a P2, and if you're looking at this frequency, this is 13 here. So these are 130 seconds on, sorry, 100. So it has a 100 milliseconds period for this SysTick handler, and this has to be multiplied by 13, so it's going to be 1 second and 300 milliseconds until it changes, until it toggles. Okay, so basically now we are in application. Congratulations to you if you stayed here so far. All I'm going to do now, I'm just going to modify this frequency. Here, let's just put it to be, I don't know, something small, I guess. How can I do it? I'm just going to ignore all these things. Just hope everything is okay. Just to, okay, so these are ignored. What I'm intending to do, just modify the application, kind of modify the frequency here, have another build, and then flash it again with our, let's say, bootloader. So how we're going to do this? Well, just modify the source file here for the application, which is program 2, and now we're going to build it, clean everything, build the new application, and then we're going to flash it, and after that the video is done. Okay, this is the new application. Control C, going here, where did I, here, put it, Control V, replace the file destination. And so this is the place where the Python shell just gets the binary. Right, so how are we going to flash it now? Because we are in the application, and this application doesn't have the possibility to overwrite itself. I mean, what we have here is still a sort of a UDS provider, but this is nothing done here so far. Probably this should be deleted. What it has, it's a reset.
So we're going to reset the thing, and after the reset it will automatically go to the, let's say, that bootloader. Why it will go? It's hard coded to start execute code from the address 0, as I previously told you. So it will take automatically the stack top from the address 0, and it will load the program counter with the address which is at 0x4, which what we have there. We have there the program 0, which is the bootloader. So now we're going just to issue this reset command in our script. Where's the script here? So this is going to be something like this. Okay, just send it, and you can see that the frequency of the LED has changed. This one means that we are now in the bootloader again, and we're going to write the application again now, right? I mean, yeah, this is test p2, this is another binary, and yeah, we're just going to flash it. Okay, and now my UDS invention, we're just going to jump to the new application, and you can see that it's indeed a new application because we have a different frequency for the LED. Thank you for your attention, and God bless.